Hey there, people. It's Mr. Dickin here. We're going to do part two of the graphing video. Oh boy. So we're going to carry on our discussion of rational functions and their graphs, dealing with holes, x-intercepts, vertical asymptotes, horizontal asymptotes, and of course y-intercepts. So without further ado, let's jump straight into the next example. We already finished the problem number one here in our part one video. Let me zoom in just a bit here if I can. And by zoom in, I mean tilt the camera even closer to the page. Okay. First thing that we want to do is always factor as far as we possibly can. When I do these, I could also figure out right away the horizontal asymptote. So actually, since we're here, let's go ahead and do that right now. I'm looking at the highest degree from the numerator, from the denominator. They're both the same. So if they're the same, that means I take the ratio of coefficients. So I have -1 divided by 1. So my horizontal asymptote here is going to be y equals 1. Okay, or sorry, whoops, -1. All right, so that's out of the way. Now let's get down to factoring. Up top, I've got a GCF of -x. And if I take that out, I'm left with x plus 1. Down below, I need two numbers that would multiply to be a -3, but add up to a -2. Those values, let's see, multiplies -3, adds up to -2, are going to be a -3 and a +1. All right, okay, off to a good start. My domain restrictions, I can't have zeros in the bottom, so 3 and -1 would be off limits. X is not allowed to equal 3, x is not allowed to equal -1, because if I plugged in 3 or -1 into my denominator, then I'd try to be dividing by 0, and if I divide by 0, the universe implodes in on itself, and everything you've ever known or loved will then cease to exist. So we cannot do that. RD, removable discontinuities. Again, I call these holes in the graph. This is anytime something cancels out, so an x plus 1 and an x plus 1, those will cancel each other out, one with the top, one with the bottom. So that means I have a removable discontinuity at -1 comma something. Well, to figure out that something, let's plug in -1. We have the opposite of -1 all over -1 minus 3. Again, I'm plugging it into the simplified version here. This would be a +1 over -4, so -1/4. And I should have mentioned at the beginning, but I think you guys know by now, if I'm going too fast or you don't understand something or you need a second to write it down, feel free to give that video a pause. All right, vertical asymptote, the VASI, it's going to be x equals something. So I look at what's left. Again, these pieces have canceled. The only thing left down below is the x minus 3, so I have a vertical asymptote at x equals 3. Just as a quick little double check, these two values from the hole and the vertical asymptote should show up in our domain restrictions, and lo and behold, they do. Excellent. X-intercept, we have just a remaining x up top, so I have an x-intercept at 0, 0, the origin. And y-intercept, well, I know the x value for any y-intercept is going to be 0, so let's plug in 0 for x, -0, so 0 over -3. Well, 0 divided by anything is still just 0. So we're going to have a y-intercept also at the origin. How fun. And then for these guys, let's go ahead and wait till we actually see the graph to do those. All right, let's get our framework down. We have a hole in the graph. A hole in the graph at -1 comma -1/4. -1, -1/4 is roughly right there. We've got a horizontal asymptote at -1, so y equals -1 is this dotted line right there. My vertical asymptote, x equals +3, it's going to be right here. Remember, we cannot ever cross through a vertical asymptote. Horizontals, we can. These just give us the general end behavior. The x-intercept, 0, 0. The y-intercept, also 0, 0. So it's kind of a 2-for-1 deal. So now, in looking at this, I can start to get the shape of the graph. I know that it's going to go through the points that I've already had established over here. So we're going to have something that approaches the asymptotes infinitely. And then over here, and for all I know, this might cross through the asymptote and kind of approach back up. It might not, I don't know. If I wanted to figure it out, I could plug in specific values, but this is the general shape. And then from here, I've got basically three options for where the other portion of this graph might be. It can't go down here because then it would fail the vertical line test, right? And it wouldn't be a function. So it's either got to be up here, kind of making this shape, or down here, making one of these shapes here. Well, if it was up here, at some point, if it's approaching that asymptote here, the horizontal asymptote, at some point it would cross through that x-axis. And well, if it crossed through the x-axis, we would have known about it. And since there's no x-intercept, because if there was, we would have known, then I can automatically assume it's got to be down here. So the other portion of this graph, it's going to get super close to the asymptotes as it goes out forever and ever. It is going to have a shape somewhat like that. So now let's get to our end behavior. What is the function value as we go really far to the right, as we go really far to the left? What is it approaching? Well, in both directions, it's getting closer and closer to my horizontal asymptote, which is -1. Yay, huzzah, we're done with that one. Just for good measure, let's do one more. If you're feeling confident and comfortable with this stuff, feel free to stop the video now and move on with your life. But if you want to see another example, have I got a treat for you? This one, the font is a little bit small, so for that I apologize. Let's give this a little camera scooting. All right, so just by looking at this, the highest exponent I'm seeing, let me write this bigger. We have 2x minus 4 over x squared minus x minus 2. The highest exponent up top is a 1. The highest exponent down below is a 2. So the numerator's exponent is smaller than the denominator's exponent. Therefore, my horizontal asymptote is automatically y equals 0. So it's automatically going to be the x-axis. And it looks like our focus is a little bit out. So we've got the horizontal asymptote. Let's go ahead and give this thing a factor. We've got a GCF up top of 2. And then down below, we're factoring down into x minus 2x plus 1. Cool. So now my domain restrictions, off limits values for x, let me switch color so we don't get backwards, would be 2 and -1. And we can't plug those values in because if we did, we'd have a 0 down in the bottom. And you can't divide by 0 because if you divide by 0, the universe implodes in on itself and everything you've ever known or loved will then cease to exist, obviously. Removable discontinuities. Let's see, anything canceling here? I'm seeing an x minus 2 and an x minus 2 from the top, from the bottom. Let's cancel those. That tells me we have a removable discontinuity at 2 comma something. To figure out that something, we'll plug 2 in for x into what's left over. So if I plug in 2 for x down here, this would be 2 over 2 plus 1, so 2 over 3. My vertical asymptote, I look at what's left over here, and -1 is what would give me a 0 in the denominator. So I will have my vertical asymptote at x equals -1. X-intercepts, how can I possibly get a 0 in the numerator? Well, if I'm not seeing any x's, I'm not seeing anything to plug into, so there are no x-intercepts. There's no way for me to turn a 2 into a 0 if there's no x attached to it. The y-intercept is always going to be 0 comma something. So let's plug in 0 for x here. We have 2 over, that'd be a 1. 2 over 1 is 2. And for these guys right here, we're going to go ahead and wait till we have our graph. Oh, we got range as well. We'll also wait for the graph on the range. All right, let's get our framework going. All right, removable, there we go, discontinuity, 2 comma 2/3. 2 comma 2/3, it's a little bit more than a half, but not quite 1. So we've got a hole there. Horizontal asymptote is at 0, also known as the x-axis. The vertical asymptote, x equals -1. X-intercepts, none. So this is very important here. That means our graph, however we draw it, is never going to cross through the x-axis. So for this particular case, our graph is not going to cut through this asymptote, because if it did, if it crossed through the x-axis, we would have known about it. Right, y-intercept is at 0, 2. So right there we've got a y-intercept. Now let's get to graphing. Well, it's pretty clear to see part of the graph is going to take place up here, mostly in quadrant 1. It'll dip over into quadrant 2 a little bit, and we've got the removable discontinuity, or the hole right there. Now we have to kind of be careful, because it might occur over on this side of the graph, or it might occur down here in the bottom left. I know it won't occur in the bottom right, because then we fail the vertical line test. So what I'm going to do is I'm just going to plug in a value here, just to give myself some reference. It looks like this is -2, so let me plug in -2 for x, just to get a point, so I can kind of base my graph off of that. If I plugged in -2 for x, that would be 2 over -2 plus 1 is -2. All right, so -2 comma -2. All right, that works. So I've got a point right here. So what that did is it helped me figure out where that graph was going to be, up top or down here. Either way is possible, so we needed to kind of look forward for that extra value. That also kind of gives me some direction as to where the curve might take place and how severe, how sharp that curve might be. So now as we go for end behavior, as we go forever to the right and left, forever to the right, forever to the left, we're getting closer and closer to a function value or a y value of 0. So we're constantly approaching our horizontal asymptotes. The range is going to represent all of the possible y values. Well, this graph goes downward forever, so it's going to go all the way down towards -infinity. And it travels upwards forever, because we have an arrow, so it's going to go all the way up towards positive infinity. The only thing that it doesn't hit is specifically the value of 0. So the way we could write this is the range is going to hit everything from -infinity all the way up to 0. And we're using parentheses because you can't actually equal infinity or -infinity. And here this is not a bracket because we never actually obtain the value of 0. And so I'm using a little union symbol, 0 to positive infinity. And what this is basically saying is every single number negative to positive infinity except for 0 itself. And the reason for that is we never actually cut through the x-axis. All right, that's it and that's all. You guys know the drill. If something doesn't make sense, shoot me an email, swing in for help, and hopefully we'll get through this unit with a strong understanding.